Hello, everyone. I'm Evan Anderson. I'm the CEO of INVNT IP, as well as the Deputy Director of Programs at the Future in Review Conference and a Senior Staff Writer at Strategic News Service. I'm here with Mark Anderson, who is the CEO of Pattern Computer. He is the CEO of Strategic News Service, so he is my boss, as well as my father. Nice to see you, as
I
always.
see you. Yep.
And today, for those who aren't used to the format of this webcast, we like to cover a lot of different subjects in the Strategic News Service Global Report, and we'll maybe talk about that a little bit more at the end for folks that aren't aware of what it is that we do. But today we're doing a fun one, so I'm greatly looking forward to this. Mark has published a number of different papers in physics focused around what he termed resonance theory. And the other day, there was some new news out of the new Webb Telescope observations that is causing quite a stir. And so we're going to get into some physics today. And I think probably first and foremost, one of the things that you recently published about that's been really important in our understanding of space, distance, et cetera, the age of the universe, is the redshift. And so for those who don't know, maybe you could just walk us a little bit through what the redshift is, why it's important, and how it's relevant to the kind of the current news.
Sure. So a long time ago, about 100 years ago, maybe, scientists noticed that particularly well understood what are called spectral lines in the light given off by hydrogen and other elements in the sky and the stars had been shifting to the red. They were redder when you looked at them from far away than they were in the laboratory, redshift. And as people who live near trains know, when a train goes by, the sound of the train, horn or whatever, whistle, gets higher as it's coming toward you, and it gets lower when it recedes from you. And that's called the Doppler shift. And the red shift is a Doppler shift. So astronomers going all the way back to about then that I mentioned, decided that the answer to why the red shift was happening, and this is a guy named Edwin Hubble, who really became most famous for this, or others, was because something was going away. The star was going away from you. And that became known as the Hubble redshift. And for 100 years, I would say roughly, people have used that idea, that theory, to explain the size and age of the universe, including the whole theory really of the Big Bang, which is the whole universe began with one Big Bang. So that idea has been, I think even until now, the main idea in understanding the world around us.
So in other words, that's how we even measured, right? That's how we even measured how fast we thought things were moving. I think a lot of people have heard, everything's moving away from us and we're measuring it. And that's hence the Big Bang. We think there's an expanding universe from an initial explosion. And you're saying that Hubble essentially decided or came up with the idea that this shift in light that we were seeing, this shift in color spectrum of light, was representative of the speed of things and the movement of things.
Exactly. And the ensuing theory and science built on that to say that we had an expanding universe because the further away things seem to be, the faster they seem to be going, the more the shift. And so there was a direct correlation which underlined or maybe self-reinforced this idea.
Okay, so maybe walk us a little bit through what's been going on with this Webb telescope. I think for most people, they've probably seen, lots of headlines about the Webb telescope. Hopefully, they've seen the images, which are gorgeous, and really, really high def. I mean, it's just stunning stuff.
It is.
So, can you talk a little bit about some of the science that's coming out of that, or at least the observations, right? What are we seeing now that we didn't see before?
Yeah. So I think the first thing to say is how exciting it is, because it took a long time to build the telescope, always does. Get it launched, get it working, tested and calibrated. And it's only been a little over a month getting images. And even if you're not an astronomer, I think it's fair to say all of us expected improvement, but perhaps not a radical new idea. That's very rare for a telescope. So great to have it be faster, bigger, better, more expensive,
Sure.
better images, all the stuff you just mentioned. We got all that. But we also got something else. And what we got was pictures we didn't expect. So a lot of argument right now. If you go onto YouTube or somewhere where we are here, I think now today,
Yeah.
You'll see people yelling at each other in quite angry terms about, is the Big Bang dead? Is it not dead? Is it modifiable? Is it good? Is it bad? A lot of emotion, a lot of heat and light, and maybe more heat than light. But people are excited, and that's worth noting right out of the bat, the whole idea that suddenly we have dramatic new discoveries, it looks like, via the Webb telescope that were kind of unexpected. So that's happening. And the Webb does this by, of course, it's modern technology. So just by saying that, it's going to be updated from the Hubble, which was the last one, last telescope, aptly named maybe. And maybe the Hubble's going to be, become less important. And the Webb is showing us, particularly in the red. So it was designed to do this. It is extremely sensitive in infrared and far red and so on, knowing that that's what we're going to be seeing for things that were farther away.
Right, and wanting to measure.
Yeah. So in line with the Hubble theory, they built the Webb wanting to find things in the red, and they did, of course. But now we have an interesting problem because the things that it's finding seem to be indicating, not just underlining Hubble's theory, but maybe making it not the only theory or not a complete theory. That's the kindest way to put it.
Yeah, so and you and I were talking about this the other day. I think it's easy for people to get into grooves, and I think there's probably lots of folks that have focused on the Big Bang with their whole career, right? And so I think it's easy for people to get into grooves where it's kind of 0 or 1, it's yes or no, it's black or white. And you and I were talking about this, and I think you had put it quite aptly when you said something like along the lines. I'm paraphrasing here, and I'll let you rephrase it if you want. But you said something like, people are talking about whether this negates the Big Bang theory, but I think it's a completely different question than that, right? I mean, go over that a little bit. What were you saying yesterday?
Yeah, and I think I'm sure that when we published the version of resonance theory, which was part 6, not so long ago, and we published other work around this question, we were careful to say what you just said. So
Mm-hmm.
this doesn't necessarily prove that there was no Big Bang or that Hubble it was wrong in any way. It's just that it was not complete. So what resonance proposes, in addition to what Hubble said, so sure, there must be Doppler. If things are moving away from us, they should have a redshift. Fine.
Right.
But what resonance proposes is, in addition to that idea, we should consider other contributors to the redshift as well. And so if the total redshift is some number, then part of that might be Hubble, might be Doppler, but part might be something else. And since resonance theory was based, since it was first created in 1980 or 79, on the idea that space itself was not empty, but was made of something, had characteristics. And those were clearly delineated. People knew what the characteristics were, even in Faraday's time. And so, okay, take that knowledge and actually stop fooling yourself, whoever you are, Mr. Einstein, and go forward and say, in fact, space is not empty. And therefore, we're going to see things in a different way than we did when Einstein first proposed special relativity, and so on. And by the way, Einstein admitted that this had been a mistake of his.
Mm-hmm.
So what we do then is say the contributors to this red shift not only are Doppler, if they are there, we don't know, but also there is a subtraction of energy as it travels along space from you to the star, or from the star to you. And so how much is that and how much is the other? We don't know. But it now appears from the new Webb findings that we have to ask these questions in a much more serious way.
Mm-hmm.
Because there are a lot of indicators that maybe the old distance theories were wrong. And they include how many new, they've looked way back now, thanks to Webb, way back to the Big Bang. Well, maybe there isn't one, but the time when they thought there was one. And so given that old theory, there are too many, apparently, too many galaxies to have been formed too early. That makes you wonder, was there a bang or not? And then the evolution of galaxies by theory until now would have indicated that they wouldn't have been as evolved as they were so quickly. That's a problem. And how many? And so you're going to get into these series of conundrums where the predictions, some people have said, of the 17 predictions of the Hubble theory, 16 are wrong. So there's a gigantic conversation now. Is that true? Or how many are wrong? How many are right? But more importantly than that, is the universe substantially different in its behavior than we thought? Is it different in its age and in its distances? Maybe its shape or its size? Are all these up for grabs?
Yeah.
And it appears that they are. It appears that they are. Yeah.
Yeah, which is probably terrifying for folks that have already written some papers about, based on existing knowledge, and probably very exciting for people who are new in the field, right? Where there is so
Yeah,
much more to
I would
discover.
guess, I would think a young astronomer would be very, very excited. She would be just dazzled and running around in circles. And older astronomers might be going, I can't believe that. Yeah.
Yeah, not uncommon. This kind of makes me think too. So it sounds like you're telling me that we may be about to learn that the universe is a lot older, not only different in nature and perhaps in distances, a lot older than we think. Are you also saying that, or are we finding with Webb observations that we may have things that are at very different distances from us than we thought?
All of the above.
All of the above.
So all of the above. And I'll keep saying we haven't done calculations to prove any particular version of this new, kind of like calling it the new model, the new model, your fancy new car, this universe number 2. But I like it a lot better, actually. So it's I think we are putting to rest, if Hubble is not the only theory that pertains, if Doppler is not the only thing that's happening, then we need to have a really good look and a deep introspection about what is this universe like, this new universe model number 2, and what are its features compared to the old car's features. And so some of the features would include that it appears that it's not certain that there was a Big Bang. Or if there was one, maybe it's a little bang, or maybe there's an ongoing series of bangs, or maybe it's not about bangs. Maybe it's more about some people have said steady state. That was a long-held theory before Hubble. I wouldn't necessarily call it steady state. I think it's extremely dynamic, but maybe that dynamism is available at all distances. Now that would be interesting. What do you mean by all? And then you get into, well, we don't know. Is it infinite? We don't know, really. Maybe it is infinite. It's hard for people to get their arms around the idea of something that's infinite, but maybe it is. Maybe it's as far as a human brain is concerned, maybe it's infinite. And maybe we're not going to see this correlation that we thought we had as a Bible, where the further it is, the younger it is. Maybe that's not true. Might not be true. In which case, we know there is distance there, but are the distances closer than we thought? Might be. Is it older than we thought? Probably. Is it different shape? Almost certainly. Is there any shape at all? Maybe it's infinite. So this new model car universe, it's shiny and it has that new car smell. It's so different that I think it'll be exciting for a long time as people figure out what's going on.
Yeah, and I think a few things are coming to mind. One, I like the kind of mimetic aspect of Universe 2.0, right? What will it look like? Particularly, since we've talked about the existing Big Bang theory for so long now that it does, it's kind of set in so many set in stone in so many different ways in writing, et cetera, and culture. So it is. I think that's very exciting. And then it also makes me think of the ant on the ball concept that we were all introduced to probably back in grade school, and just kind of that whole issue of perspective, right? So.
Yes. I think that was an embarrassing moment in science. I know that the person, when the expanding universe was first proposed by a scientist, I don't remember his name, he was ashamed and embarrassed, apparently. He didn't want to publish it because it was so crazy. And so now perhaps we can help put him to rest that, maybe that didn't happen. There was no balloon expanding and there was no ant.
So, maybe just for the folks that haven't read resonance theory, can you go a little bit deeper into what you were talking about when you published those things? I mean, at the time, particularly in the 80s when you first started publishing them, but even just recently, the pieces that you put out in the spring, et cetera, have all been, pretty different from what's going on in the world of ivory tower physics. So maybe talk a little bit about that and kind of explain what you're talking about when you're referencing it.
Sure. Two main things here. The most important part is, which we work on a lot at Pattern Computer, but is that using pattern recognition to do science or mathematics is orthogonal to what you would do normally. So normally, I went to Stanford. Normally, you go to school, university, they would teach you what the other guys knew. Here's what the other guys think until now. Now you memorize that and go forward. Well, that's a pretty constrained world of discovery there you got, so you're not going to really break any glass back 100 years ago doing that.
Yeah,
And
incremental
that's a really big
improvement.
problem. That's a big problem. Yeah, that's a big problem. You want to get an A, do this, So contrary fashion, if you come into it cold and don't know anything, you didn't have to go through all that, and you use pattern recognition to try to understand what has been learned so far based on experiment, just based on experiment, you might come to some completely different conclusion or different finding.
Mhm.
We call that a pattern discovery. You may make a major discovery that was not, it was before everyone, but not available for cultural or academic, cultural, or who knows reasons. And so as a freeloader, an amateur, all the great scientists in the earlier days were all amateurs. Newton was an amateur. So, all these very famous people were amateurs. So I think that's a fair thing to be. And coming at it from a pattern recognition perspective is almost guaranteed to give you a different view of that science or that series of events or experiments than you would have had if you were taught at Princeton. And so that's the beginning of the whole resonance program, was doing that with force laws and with light, and trying to figure out light, which still remains a beautiful mystery today. So by doing that, I ended up having a different understanding of what space was, because I convinced myself pretty quickly that it couldn't be empty. And so if it's not empty, what is it? And we always joke about it being called yellow jello. It's yellow jello in there. But whatever it is, it has what used to be called ether. You're not allowed to say it anymore, but it is substantial in some way or other. It has physical characteristics which are easy to measure. And like I said, have been known since Faraday's time or near then. So, okay, that's easy. And then you go forward from there. And once you accept that space is not empty, all kinds of interesting things are available as discoveries. And then, so I published these, I think there have been 8 papers now, or 9. And 3 of them just in, I think, 6 or 8 weeks this last year. And one of them, number 6, was about this subject of dark matter, dark energy, and the cosmos, and all that stuff, including now, reassessing the redshift.
Yeah. And I think it is intuitive. We've talked about this before, but I think it is intuitive that you would need to know what a substance is that you're looking through in order to figure out what it's doing to the image of the thing on the other side, right?
Sure,
and that's not an
that's
uncommon concept with light and matter. It's
right.
something we observe all the
Right.
time on Earth, when we're looking through bodies of water, right? Looking down through the surface of a lake, everything's
Mhm.
distorted, and we know it, right? So we're aware that happens. So
Yeah.
it does follow logically that may be happening in other ways around us too.
It does. As I think you know this, but maybe those watching don't. I published a fairly risky paper called Einstein's Biggest Mistake, and it wasn't what everybody always thinks in school, which is his cosmological constant, which is more about the expansion of the universe. That was another mistake. But his biggest mistake, I said, was thinking that there was no ether.
Yeah.
That their space was not substantial. And he later, I found out after I'd written that, through Walter Isaacson, who's his biographer, who's a friend of mine. He later said that himself, and he gave a speech at Leiden, University of Leiden, saying that was his biggest mistake. He shouldn't have said it. And so, as you're discussing with water or with anything else, he should have realized you have to have a medium if you're going to have a wave.
Yeah. Yeah.
Space-time itself was not enough. So he did something which harmed his own studies, his own future. It prevented him from ever achieving his most important personal goal, which was a unified field theory. You couldn't get there without having space have substance.
Well, that's just
Yep.
one more exciting thing, is that perhaps, it sounds like what you're saying is perhaps this is one little step and maybe a long journey towards something closer to unified field theory, right?
Yes, I think that's right. Much closer. Yep.
So I'm going to wrap this back around, just because we have a broad audience and we want to make sure that we're not so, that's super fascinating. If
We're
I'm
down
just
in the weeds here.
Yeah, if I'm just some person walking down the street, what do you think the implications of all of this are, right? So what is going to change in my world in the next 5 years based on these web images and this new understanding?
Well, I think it's where we started this conversation. I don't expect a person on the street in any country in the world to care that much on a scientific basis. They don't stay up at night worrying about things like this. But people are affected, I think, who are normal people, not science. I think they are affected in an emotional and spiritual way by these things. And there may maybe two ways. One would be if you're living in an open universe compared to a closed one that's slowly expanding, that's a different feeling. And if you maybe the idea that we've discussed these different ideas will give some kind of an emotional or spiritual lift to people. Is the universe infinite? That's a different feeling. I just got to tell you, your neighborhood is infinite. It's not a little box or a little shape, some kind. So maybe that would affect how people feel about the whole world. And then, maybe equally exciting would be at a time when I'm going to make a statement which is be a little rough, but I think that big science isn't very good. It's for the reasons we talked about today. It's so canalized that really big discoveries are few and far between. Maybe not in bio so much. A lot of bio going on, but other than that, in physics for sure, it's pretty constrained. You put 200 people on an experiment, and you find some little thing that nobody really cares about. So, and that costs $20 billion, and 100 people on the paper. That's embarrassing, I think. So, back in the 1920s, 100 years ago, it seemed like every 10 minutes there was a major discovery, theoretically. Well, we haven't been living in that world for 100 years. And maybe one of the great benefits of this for people would be we still live in that world.
Yeah. We're still capable of discovering completely new things that change the entire equation, right?
Yeah. There are still really big things out there to find, really, really big. And I think that would make people happy.
I know it makes me happy. I think that's a good note to end on too. And hopefully this has been, we talk about a lot of different things, like I said, on this podcast. So hopefully this has been kind of a hopeful and happy and interesting episode. And for those who don't know, Strategic News Service is available by subscription online. So you can go to www.stratnews.com. We're essentially a lot of different things. So for those of you who like to learn about the world, learn about what's going to happen in the next 3 to 5 years, that is our specialty. We have accurate predictions about geopolitics, technology, economics, and physics, as it turns out.
Yeah.
So thank you, Mark, for your time, and pleasure as always. And I will see you all soon, hopefully.
Thank you.